So in this section, we're going to talk about the relationship between matrices and linear transformations. So the core idea is that matrices are functions. So let's look at the following example. So suppose that A is given by this, and X is here and Y is here. Then we can certainly calculate the matrix vector transformation. So AX is given by 2, 3, -1, 4, 0, -5, -2, and 1. And we can certainly multiply this by 1, 1, 1, 1. Then this gives you, well, I guess the first row is like just 2 plus 3 minus 1 plus 4, which is 8. And the second row is 0 minus 5 minus 2 plus 1, which gives you a -6. At the same time, if you multiply y by the matrix A, then that gives you, then the first row is 2 times 0 plus 3 times 2 plus -1 times 3 plus 4 times -1. And the second row is 0 times 0 plus -5 times 2 plus -2 times 3 and 1 times -1. And if you calculate this matrix, you get 6 minus 3 minus 4 and -10 minus 6 minus 1. That gives you -1 minus 17. So the point is, if you multiply vector by a matrix, then starting from R4, we have X here and Y vector here. Then these two vectors get mapped by A into two-dimensional place because the result for this multiplication is two-dimensional vector. And X is gets sent to 8 and -6. And Y is gets sent to -1 and -17. So basically, we can regard the matrix multiplication A as a function from R to the N to R to the M, where X is sent to A times X. So here, we call that this A as a function or mapping or transformation. And R to the N is the domain of the function. And R to the M, and we call that as the codomain. And here, the vector X is an element of the domain, and A times X is called as an image of the vector X. So basically, the domain and codomain really tell us the size of A. So if you go to the previous example, then we know that the matrix A is 2 by 4 matrix. And you can tell that the element of the domain or the domain of this function belongs to R4 that matches with the number of columns here. And the result, the image of the given vector synthesized to R2, where this 2 corresponds to the number of rows of your matrix. So range tells us the number of rows, and domain tells us the number of columns. Okay, so in this exercise, we have a matrix given by A equals to 2, 0, -2, 5, 1, 3, and we have 3 different vectors. So let's pause the video and try out the part A and the part B and part C of this exercise. Okay, so let's solve this problem together. So for the image of U under A is by definition that is the same as A times U. So AU is the same as 2, 0, -2, 5, 1, 3 multiplied by 1 and -1. And this gives you 2, -2, -5, 1 minus 3, which gives you 2, -7, and -2. Okay, so for the part B, we have to find out X inside the domain such that if you multiply by X, you get the vector B. So what I mean is we want to solve for X such that X satisfies this equation. And if you plug in A, X, and B into this matrix equation, then This is equivalent to say we have to solve for this equation. So if you think about an augmented matrix, which is given by 2, 0, 0, negative 2, 5, 10, 1, 3, and 6, then it is row equivalent to, so basically we can divide by 2 for the first row and then subtract this from the other rows, which gives you 1, 0, 0, 0, 5, 10, 0, 3, 6. And this get reduced to 1, 0, 0, 0, 1, 2, and 0, 1, 2. That gives you 1, 0, 0, 0, 1, 2, and 0, 0, 0. So here, this tells you that, so we have x1 equals to 0 and x2 equals to 2, which means we have the unique solution. And for part C, we have to find whether C is inside the range of A. So this is equivalent to ask whether the given vector C is the image of some vector x in R2. Or in other words, we need to determine whether we can find x such that AX equals to the vector C. Again, to solve for x, we want to use the augmented matrix technique. So if you form the augmented matrix using C, then that gives you 2, 0, negative 5, negative 2, 5, and 10, 1, 3, and negative 6. So first of all, I'm going to switch the first and the last row. That gives you 1, 3, negative 6, negative 2, 5, and 10, 2, 0, negative 5. And then I'm going to multiply by 2 for the first row, and then add and subtract from each columns. So that gives you 1, 3, negative 6, and I guess 0, 11, and negative 2. And for the last row, we have 0, negative 6, and 7. Now, to cancel out this part, we're going to multiply by 11 into R3, and then add 6 times R2. Then that gives you 1, 3, negative 6, 0, 11, negative 2, and 0, 0, and 65. So here, the last row gives you 0 equals to 65, which is inconsistent. So we can conclude that the vector C is not in the range of the given matrix A. So let's look at several examples about the matrix transformation. So for the first one, A is given by this, which is 3 by 3 matrix. So we can tell that, well, A is from R3 to R3, that is defined as sending X into A times X. So here, A times X equals to 1, 0, 0, 0, 1, 0, and 0, 0, 0 multiplied by x1, x2, and x3. That gives you x1 and x2 and 0. So if you graph these two vectors in R3, then we have so x1 and x2 and x3 here. And let's say your vector v was here in the beginning. Then a times x or a times v projects the given vector into x1 and x2 plane. So we can conclude that A projects vectors or points onto the x1, x2 plane. So we have another example for A is given by 2 by 2 matrix, 1, 4, 0, 1. So you can tell that, well, the domain for A should be R2 because the number of column is 2, and the range for this map is also R2 because the number of rows is just 2. So to visualize how A acts into elements in R2, then it is easier to see when you work on what A does to the given unit square. So let's multiply A into each vectors. Okay, so here, well, the first row should be 1 times 1 plus 4 times 0, which gives you 1. And 1 times 0 plus 1 times 0 is 0. And second, I guess we have 1 plus 4, which is 5, and 0 plus 1, which gives you 1. And this one equals to 4 and 1. The last one is simply 0 and 0. So basically, from these four results, we can tell that A moves the unit square into 1, 0, 5, 1, and 4, 1, and 0, 0. So we get this tilted square. And we call this kind of transformation as a shear transformation. So here, the big idea for this section is that matrices are linear transformations. So here, what it means for the linear transformation is that, so we call the transformation T is linear if, well, first of all, we should be able to split the addition in this way. And second, we should be able to factor out the scalars. And we can certainly tell that the matrices fit these two criteria. So you want to pause the video and give it a try by yourself before I give you the solution. Okay, so did you figure this out? So in section 1.4, we've seen that the matrix vector product satisfies the distribution law. So A times U plus V equals to A times U plus A times V. And also, we've seen that we can factor out a scalar that is multiplied into the given vector U. So A times CU equals to AC times AU. So this proves that matrix products satisfy the linear transformation law. Okay, so there are some properties about the linear transformation. So first of all, if you put 0 into T, then we get 0 as a result. And this is because we know that 0 equals to 0 plus 0. So T of 0 is the same as T of 0 plus 0. And from the first law, we know that we can split addition over here. So this equals to T of 0 plus T of 0. And if you cancel out T of 0s for the both sides, then this gives you T of 0 equals to 0. In part B, well, we can first split the addition and then factor out C and D. And part C is the generalization of the part B with various vectors with their weight.